In this class, we will prove few theorems on continuity. Number one is Bolzano's location of roots theorem. So at first, starting with the statement of the theorem, we have f from close AB to R be a continuous function. F is a function defined on close AB to R, which is a continuous function, and fa, fb are of opposite signs. That means one is positive, another one is negative. Then there exists at least a point C, at least one point C belongs to open AB such that FC equals 0. That means whenever we get one continuous function defined on a closed bounded interval such that the signs at the end points, that is FA and FB, are different, then there exists at least one point C belongs to AB such that FC will be equal to 0. That means it is basically geometrically it is saying whenever we will get one function such that its endpoints are of opposite sign, that means it has a root between these 2 points A and B. If we try to get the graph of the function like this, suppose this is the 2-dimension x-axis, y-axis, okay, and it is saying FA and FB are of opposite sign. Let's take FA is positive, FB is negative. Then suppose this is the point A and this is the point B. Okay, FA is positive, that is here somehow is FA. Okay, and FB is negative, so somehow here it is FB. This length is FB, and here is the graph like this. That means there exists at least one point C belonging to open AB such that FC cuts the x-axis, that is FC equals to 0. That means C is a root of the function fx equals 0. Okay, this is the geometrical interpretation of Bolzano's location of roots theorem. That means when the points are different in sign, the functional value of the points are different in sign, that means there exists a root between them. Okay, similarly the same thing will happen if FA is negative and FB is positive. Then the graph will be a little bit different like this. Suppose this is A, this is B, FA is negative, choosing here somewhere FA, and FB is positive, here somewhere FB. So graph is like this. Here is the point C such that FC equals 0. FC cuts the C. At the point C, the function f is cutting the x-axis. Okay. So this is the geometrical interpretation of Bolzano's location of roots theorem. Now we have to prove it. Proof is very easy. First we are choosing the interval close AB where the function is defined as I1. Okay, the interval close AB as I1. This is A, this is B. Now we have two conditions in our hand. Number one, f is continuous on the domain close AB, and number two is FA and FB are of opposite sign. So that means either FA is positive and FB is negative, or FA is negative, FB is positive. So without any loss of generality, we are choosing the options one by one. First we are choosing let f of A is less than 0 and f of B is greater than 0. Okay. Now we are naming this interval AB as A1, B1. Renaming the interval as A1, B1. That means f of A means f of A1 which is less than 0, this one, and f of B means f of B1 which is greater than 0. Now we are dividing this interval at the midpoint. Suppose the point is C1. That means C1 is equals A1 plus B1 by 2. Okay. Now here three cases can arise. Number one, f of C1 is equal to 0. Number 2, f of C1 is greater than 0. And number 3, it is less than 0. Now check if C1 is equal to 0, then there is nothing to prove because we already get one point C1 which belongs to open interval A1 B1 such that f of C1 is equal to 0. That means we got our root. Okay, there is nothing to prove. So for this case the theorem is done. Now check the next case. Either it is greater than 0 or it is less than 0. Now if it is greater than 0, then we are choosing a1 comma c1 as our new interval such that f of a1 is less than 0 and f of c1 is greater than 0. And f of c1 if less than 0, then we will choose c1 comma b1 as our new interval such that f of c1 is less than 0 and f of b1 is greater than 0. That means whatever sign it will take, we will choose it with left end point or right end point such that for our new interval a2 b2 the signs at the end points are different. Okay, so if this happens, then we will choose a1 comma c1 as our new interval. Okay, and if this happens, this is less than 0, then we will choose c1 comma b1 as our new interval such that we want to make the signs at the end points are different, are opposite actually. So in any case we were choosing either this or this as our new interval and naming it as I2 and taking it as A2 comma B2. Okay, that means either A2 B2 is either A1 C1 or C1 B1 according to it is depending on the sign of f of C1. Now check for this I2. What we can say about this I2? Number one thing, f is continuous on I2, right? And if we choose the first case, then f of A2 is less than 0 and f of B2 is greater than 0. Okay. Number 2, I2 is a subset of I1 because we just take the middle point of A1 B1. Number 3, what is the length of the interval I2? The length will be the half of the length of the interval A comma B, that is B minus A by 2. Okay, so these 3 points we can claim about I2. Now moving to the new interval I2, that is A2 B2. This one A2, this is B2. Again we are dividing it at the midpoint and naming the point as C2. So what will be C2? C2 will be A2 plus B2 by 2. Then here also 3 cases can arise, that is f of C2 either 0 or greater than 0 or less than 0. And we have already chosen the case where f of A2 is less than 0 and f of B2 is greater than 0. You can take the another option also, that is f of A2 greater than 0 or f of B2 less than 0. I am choosing it here just for the generality. Okay, so if f of C2 is equal to 0, then check there is nothing to prove because we got our root, the point where the function cutting the x-axis. That means the theorem is done for f of C2 is equals to 0. Now if f of C2 is greater than 0, then what will you choose? This is less than 0, this is greater than 0. That means in that case we will choose A2 C2 as our new interval such that f of A2 is less than 0 and f of C2 is greater than 0, opposite in sign. Or if f of C2 is less than 0, then we will choose this length as our new interval C2 comma B2. Okay, then f of C2 will be less than 0 and f of B2 will be greater than 0. That means opposite in sign. So in any case we will choose either this interval or this interval and renaming this interval as A3 comma B3. So we are taking in the next line, we are writing in any case we get new interval I3 equals A3 comma B3. Okay, we can claim about I3. Number 1, f is continuous on I3, and we are choosing f of A3 is less than 0 and f of B3 is greater than 0. Okay, you can choose the other case also. I am choosing it here. Number 2, I3 is a subset of I2, which is a subset of I1, right? We are just dividing the intervals. And number 3, what will be the length of I3? It will be b minus a by 4. That means at first we divide b minus a, then taking one part we are again dividing it. That means b minus a by 4, that is b minus a by 2 square. Okay, these 3 things we can claim about I3. Now again taking the interval I3, we are again considering the midpoint, naming it as some C3, and again choosing either this interval according to the sign of C3 and either this interval according to the sign of C3, and making new interval I4 and so on. Okay, so by applying this iterative method, at last what we will get a sequence of closed and bounded intervals in, right? Applying the same method, we get a sequence of closed and bounded intervals in such that number 1, f is continuous on in and f of an less than 0 and f of bn greater than 0. Number 2, in plus 1 is subset of in, that is I2 is a subset of I1, then I3 is a subset of I2 which is a subset of I1, and so on. And number 3 is the length of in is b minus a by 2 to the power n minus 1, because the length of I2 was b minus a by 2, then I3 b minus a by 2 square, and so on. So the length of in is this. Now we can apply over this set of intervals or the sequence of intervals, we can apply the nested interval theorem. So by applying Cantor's nested interval theorem, what we can say? That there exists only one point alpha such that alpha belongs to all in for all n belongs to natural numbers, that is alpha belongs to I1, I2, I3 and so on. Alpha belongs to all in, and limit of an equal to alpha and limit of bn also equal to alpha. Just by applying Cantor's nested interval theorem, we can claim that this quantity, there exists only one number alpha such that alpha belongs to in, and limit of an is equals alpha and limit of bn is equals alpha. Now whenever we say that alpha belongs to in for all n belongs to natural number, that means alpha belongs to close AB, right? And f is continuous on close AB. It is given in the question. That means f is continuous on alpha. Okay. Again, check the sequence an. That is all a1, a2, dot dot up to an. This is a sequence of points in close AB, right? And which is tending to alpha as n tending to infinity. We have checked that limit of an is equals alpha. That is the sequence an is tending to alpha, and f is continuous at the point alpha or continuous over close AB. That means by sequential criteria, what we can say that f of an, this sequence will tend to f of alpha by sequential criteria of continuity. And we have also checked that f of n is less than 0, right? We got this from this nested sequence. That means its limit will also be less than 0, that is limit of f of n will be less or equal to 0. That means f of alpha will be less or equal to 0. We can get this. Okay. Again we got the sequence Bn also over close AB, such that Bn also takes the limit alpha as n tending to infinity. Then by the same sequential criteria of continuity, what we can say, f of Bn, this sequence also tending to f of alpha, right? Again, f of Bn, this sequence is greater than 0 for all n. We got this from the nested sequence. F of Bn is greater than 0, that means its limit of f of Bn will also be greater or equal to 0. That means f of alpha will also greater or equal to 0. We got this one. Now combining this one and this one. This is once less or equal to 0, again greater or equal to 0. That means combining these two, what we can say, f of alpha is equal to 0. Okay. That means we got our point alpha, which is our actual C for our theorem. That means this is our C such that fc equals 0. We got one point alpha belongs to open AB such that f of C or f of alpha is equals to 0. That means whenever the two endpoints are of different signs, opposite signs, that means there exists one root between the point of the function.